cloud. Okay, so I'm recording that, this session. And I will keep an eye on participants and try to admit anybody who comes on a little bit later. And in the meantime, we've got 3 people here. So I am happy to answer any questions you'd like to ask about any of the homework problems, quiz problems that we've done, practice exam problems, whatever you want to ask about.
Let me get the book up. I think I still have some more questions from that, so.
Okay.
Can we look at 62 on in the book?
What chapter?
10.
Okay, chapter 10, problem 62. I'm opening it up in Wiley Plus here, and then I'll read it. Okay, so chapter 10, problem 62. It says, in the figure they provide, I'll draw a picture of this thing. What we have are 3 particles, and they give us the mass of them, and they've been glued to a rod of a given length. The rod itself has negligible mass. And that structure can rotate around a perpendicular axis through point O at one end. So here's what the picture looks like. You're looking down from above. There's point O. There's part of the rod. There's one of the particles, mass M. Then the rod continues. And there's another particle, mass M, and then the rod continues. And then a third particle, mass M, at the very end. The distance here they call D, and here is D, and here is D, and this total length is L. Now here's what they tell me. The M of each particle, I'm using the numbers here on Wiley Plus, 0.0100 kilograms. And the L length, I'm told, is 6 centimeters. That's how they say, that's how they give it to me, that information. And this whole thing is going to rotate about this axis coming out towards us through O. And it's going to rotate in the plane of the screen, like that, for example. Counterclockwise, if you like, about O, that whole thing, going around and around and around. Okay. So we are asked, how much work is required to change the rotational rate from 0 to 20 radians per second, and then from 20 radians per second to 40 radians per second, and from 40 radians per second to 60 radians per second? And then what is the slope of a plot of the assembly's kinetic energy in joules versus the square of its rotation rate? Okay, that's interesting. All right, well, basically what this reminds me of, since they ask about work, is work kinetic energy theorem. Total work equals change in kinetic energy. And this is the thing they're asking. Whoops, didn't mean to do that. Let me get that back. This is the thing they're asking for, work. And so hopefully I can get it by finding the change in kinetic energy of this structure. So let's focus on that. Of course, delta K means K final minus K initial, or K2 minus K1, however you want to say it, where K in general for an object that's rotating is 1/2 I times the angular speed squared. That's the formula for rotational kinetic energy. And we're not changing the shape of this thing as it rotates. So the I part, the rotational inertia, that's not changing. That's constant. What's changing as we do work is how fast the thing rotates. That's the omega, which in this context means the angular speed. So when they write the delta K, when I write the delta K, K2 minus K1, I mean 1/2 I omega 2 squared minus 1/2 I omega 1 squared. Because it's the omega, it's the rate at which it's rotating that's changing. And I'm inclined to factor on the right-hand side the 1/2 I and write it as omega 2 squared minus omega 1 squared. Now that is getting me set up closer to the kind of information they give me in this problem. Because in part A, they want to change the rotational rate, angular speed, from 0 to 20 radians per second. So that means put 0 in for the omega 1 and 20 radian per second in for the omega 2. And we've dealt with that omega 2 squared minus omega 1 squared. So all we really have to then find is the I. What is the rotational inertia for this object about the axis at the end O? Well, what we really have are 3 particles. It tells me they're particles. And the formula for the rotational inertia of a particle is mass times distance squared. Oh, sorry, I got another person to admit here, okay? So I need to work out the formula for I, the rotational inertia of this structure about point O. So I'm going to take the mass of each object times its distance from the axis O squared. Now every object of the 3 particles has the same mass, but they are different distances from O. That's what's going to have to keep track of. So for the first particle, the one closest to O, its contribution to I is md squared. It's got mass m and it's a distance d from O. But there's more. The second particle, the one in the middle, has mass m, but how far is it from the axis O? It is a distance 2d. So I have to do 2d quantity squared times m for the middle particle. And then for the particle on the very edge, the outer edge, it's got a mass m, but it is a distance 3d. So I have to take 3d quantity squared. So let's get what that is. So that's md squared plus 4md squared plus 9md squared. What is that? 9 and 1 is 10 plus 4 is 14. So 14 md squared. There's the I, the rotational inertia for this object, whatever you want to call it. And that I is not going to change. All that's going to change is that we're doing work on this thing somehow, cranking it, if you like, somehow. And it's just spinning faster and faster. That's what's physically happening. So to find out how much work we do in part A, I'm going to plug into this formula right over here. 1/2 I times omega 2 squared minus omega 1 squared. So 1/2 times 14 md squared times omega 2 squared minus omega 1 squared. I guess we can write that as 7 md squared times omega 2 squared minus omega 1 squared. Now the d, we can look at our picture. Each d is L over 3. And L is what they give me. So let me put that in next. 7m times d, but d is L over 3, so I square that. So omega 2 minus omega 1 squared. So I'm getting this as simple as I can before I plug in numbers. Because I have a 3 squared downstairs, that's 9. So 7/9 ml squared times omega 2 squared minus omega 1 squared. Now I would plug in numbers. Let's be clear what the numbers are going to be. Omega 1 is 0. Omega 2 is 20 radians per second. The L, gotta be careful, my number here is 6 centimeters. So I have to enter that as 0.06 meters. And each M is 0.01 kilograms. So that goes there. Let's see what I get when I put that in my calculator. 20 squared minus 0 times 7/9 times m, 0.01 times 0.06 squared. So I get that the work we have to do is 0.0112 joules. And we have done part A. Now, that part B says, how much work do I have to do to change the rotational rate from 20 to 40? So I just used this same formula I just did, except I change the omega 2 and the omega 1. The omega 2 is now 40 radians per second squared, and the omega 1 is 20. Okay, because now we're changing from 20 to 40. Well, 40 squared minus 20 squared, and then times 7 divided by 9 and times m and times L squared. And I get 0.0336 joules. And what is part C? Part C is another change in omega from 40 radians per second to 60. So now the final is 60. So omega 2 is 60, so that gets squared. And the omega 1 is 40, so that gets squared. Let's see what that gives. 60 squared minus 40 squared times 7 divided by 9. The m is 0.01, and then L squared is 0.06 squared. And now I'm up to 0.056 joules. Okay, so even though I'm changing in 20 radian per second increments, first from 0 to 20 radians per second, then from 20 to 40 radians per second, then from 40 to 60 radians per second, The amount of work is not the same for each one because the work doesn't depend on omega to the 1 power. It depends on omega squared. And the last thing they asked me to do is, or the last question they asked me, what is the slope of a plot of the assembly's kinetic energy in joules versus the square of its rotation rate? Well, that's the formula I had right up above. The kinetic energy is 1/2 I omega squared. So if I were to make a sketch of kinetic energy versus rotation rate, that's angular speed. No, square of rotation rate, I beg your pardon. Then if I plot K on the y-axis and omega squared on the x-axis, is kind of like playing the match game in lab. That's now y, and omega squared is now x. And so that is just a constant. Notice what that is. That's the equation of a straight line. It's going to be a straight line of positive slope A, and that slope is 1/2 I. So the slope of that plot will be half the rotational inertia. And we could get a number because we've got a formula for the rotational inertia. Oh, I've got it written up there. There it is, 14 md squared. So the slope A of that plot of K versus omega squared is 1/2 of I. So that'll be 7 md squared. Let's plug in numbers. 7 times m is 0.01 kilograms. D is L over 3. I guess I should write that. So that's L over 3 squared. So that's 7/9 ml squared. That's what I want. And the L is 0.06 squared. And yep, so I get 2.8 times 10 to the minus 5. And that would be kilogram times meter squared. But the point is, if you were to plot K versus omega squared, you'd get a straight line. So that would be that last part, which might seem a little odd, part D, is exactly like what something we might do in lab. We might make a structure like that somehow, and we might spin it at a specified rate, maybe with that stepper motor, and then we could plot K versus omega squared, get a straight line, use the slope to figure out what the rotational inertia of that thing is. And there's the cat. And you walk right on by. Okay, so that's chapter 1062. Does anybody want to ask a question about what I did there? Okay, hearing none about that, would anybody like to ask a question about a different problem?
Could we do 62 on chapter 11 this time?
Chapter 11, okay. Okay, let me bring that one up. Okay, chapter 11, number 62.
Yeah.
Okay. I don't think that was one of the homeworks, but I'm willing to do it unless I'm misunderstanding.
I
Is
was
it
just looking at it. It's not
okay?
the homework.
Okay, that's fine. We can look at it. It looks like a kind of a trapeze, doesn't it? Trapeze problem. Let me see here. Oops, let me get myself some room here. And we'll do a aerial trapeze problem. Okay, here's what it says. During a jump to his partner, an aerialist is to make a quadruple somersault, lasting a time t of 1.87 seconds. For the first and last quarter revolution, he is in the extended orientation shown in figure 1133 with kind of his body just straight out. And he's got a rotational inertia I1, 19.9 kilogram meter squared around his center of mass, which is represented by a dot in the figure. During the rest of the flight, he is in a tight tuck with a smaller rotational inertia of 3.93 kilogram meters squared. What must be his angular speed omega 2 around his center of mass during the tuck? Okay, that's a very interesting problem. So let me try to draw some pictures. We got a kind of a combination of things going on. Here's the release point. If we follow his center of mass, it is only being influenced by the gravitational force. There's where he's released, or where he lets go of the bar. And here is where he is caught. That little arc I just drew there is the trajectory of his center of mass. And that's a parabola, and that's just projectile motion. Okay, and we know how much time he's in projectile motion. I'm going to call it delta t. 1.87 seconds from release to catch. Okay, now during that time, he does 4 rotations about his center of mass. Because he calls it a quadruple somersault. So I interpret that to mean 4 rotations around the center of mass. Now, okay. For the first and last quarter revolution, all right, so that's 2. So let's think about how many quarters that is altogether. That's 4 times 4. That's 16 quarter revolutions. As I just think it might be convenient to think of it that way. Okay, there's 16 quarter revolutions since he does 4 rotations or revolutions. I could say a rotation. Okay, out of those 16 quarter revolutions or rotations, 2 of them are in the extended orientation with the larger rotational inertia because the body is more like a straight line. And that I1 is 19.9 kilogram meter squared. And then the remaining 14 of the quarter revolutions are in what's called the tuck orientation, where the rotational inertia is smaller because he's kind of tightened up in a ball. And that rotational inertia is only 3.93 kilogram meter squared. Okay, so we've got 14 quarter revolutions in a tuck and 2 quarter revolutions extended. All right, and he's got an angular speed omega 1 when he's in the extended orientation. And it's going to be a higher angular speed omega 2 when he's in the tuck orientation. I can see that. And what I need is I need to complete these 16 quarter revolutions in a total time of 1.87 seconds, because that's when he's going to be caught. And he has to have just completed them by that point. Now, the key thing here is that as this aerialist, as he's called, is doing his somersaults through the air, the only force acting is gravity. Gravity acts at his center of mass. Therefore, the gravity can't produce a torque about the center of mass. So the angular momentum about the center of mass can't change. Because while there is a force acting, F grav, there is no torque from that F grav about the center of mass. So the angular momentum about the center of mass is always the same. And that means when the person is in the extended orientation with the larger rotational inertia, or when the aerialist is in the tuck orientation with the smaller rotational inertia, in both cases, they have to have the same angular speed, same angular momentum. So here we go. For the initial and final, I'm just really going to call this extended and tuck, because those are kind of the two key situations. Is the body extended or is the body in the tuck orientation? So for the extended, that's an angular momentum of I1 omega 1. Remember, for an extended body, angular momentum is I times omega. And in the tuck orientation, the angular momentum is I2 omega 2. So the product, I1 omega 1 must equal I2 omega 2. So what I can learn from this is how omega 1 is related to omega 2. I think that's what's going to be helpful. Omega 1 is going to be I2 over I1 times omega 2. Okay, so that's going to be helpful. I'll number that equation, I guess, equation 1. All right, now let's figure out how to get this timing the way we want it. I want 2 quarter revolutions and 2 quarter revolutions at omega 1 and 14 quarter revolutions at omega 2. And a quarter revolution is pi over 2 radians. So if I complete, so let me do it this way. 2 quarter revolutions each one of those is a quarter revolution. That's going to be pi over 2. In the extended orientation, plus 14 quarter revolutions. I'll just call this delta theta. Those are also. That's what I want to complete. That's the amount of angular displacement I want. And I want that completed in a total time, delta t, of 1.87 seconds. Well, that's, okay, so that's fine. Now, how much time to complete these? Let me see, complete these revolutions. Well, The extended ones, right here, are completed at the rate omega 1. And the tuck quarter revolutions are completed at the rate omega 2. So I want the total time to complete the 2 extended quarter revolutions and the total time to complete the 14 tuck revolutions to equal 1.87 seconds. I think I want to do it that way. Okay, now the delta T1, that time, that will be the amount of rotation, 2 times delta theta, 2 times pi over 2, over omega 1. And for the delta T2, I have 16 quarter revolutions completed at the rate omega 2. And that total amount of time must be 1.87 seconds. Oh, I have somebody else here to join, to admit. Okay. Okay. Now, I'm going to combine this expression with equation 1, which enables me to write omega 1 in terms of I2 over I1 times omega 2. So I think I've gotten this down to with one unknown only, but let's see how the math turns out. Let's look at this a bit more. That 2 cancels that. That 2 cancels part of that, leaving me an 8. So let's see. I have pi over omega 1 plus 8 pi over omega 2 must equal 1.87 seconds. If we want to factor the pi out, we can. And for the omega 1, I'm putting in I2 omega 2 over I1. And then I have an 8 over omega 2. Now I'm going to factor the omega 2 out front. It'll be downstairs though. And now I'm going to solve for omega 2. So I'll get pi, let's see, I'll get pi times I1 over I2 plus 8 all over 1.87 seconds. There's a radian, by the way, with that pi. So omega 2 is going to be in radians per second. So this is pi times I1 over I2. That's 19.9 over 3.93 plus 8. All over 1.87 seconds. Let's just see what this is. 9 divided by 3.93. That's 5.06 for that ratio right there. Then add 8. Then multiply by pi. Then divide by 1.87. And it turns out this person is, and this is the high speed part. Omega 2 is in the tuck position, 21.9 radians per second. That's quite a clip. That's what I get. Now, I haven't double checked all my math, but I think that's the general idea. Now, that's a challenging one. If you look on Wiley Plus at the end of chapter 11, you'll see that problem has 3 stars beside it. It's got 3 little stars right there beside it. That means it's challenging. So that one would definitely be one you probably would have to sit and think about. But it is, probably one of the reasons it seems a bit challenging is because it's real world. Now, the aerialist learns how to do all this computation by practice, not by studying physics, of course. Although you could, I suppose. In any event, that's how I have done that. Is there any questions about what I did there? That's a challenging one.
Could we also go over 15, chapter 15, problem 22? It's on our homework for this week.
Okay. Let me look at that one. Okay, now we're into the chapter on oscillations. Okay. 1522. All right. We are given a figure that shows a block 1, and we're given its mass. And it's sliding to the right over a frictionless elevated surface at a given speed. Let me start drawing the picture. All right. Here is block 1. Traveling to the right over a frictionless elevated surface. And I know how fast, V. And I know its mass. I'm going to call this M1, okay? All right. This block undergoes an elastic collision with stationary block 2. There's block 2, initially stationary. And they don't tell me its mass. That's interesting. But they do tell me that block 2 is attached to a spring of spring constant K, and they do tell me K. We are to assume that that spring does not affect the collision between the two blocks. After the collision, block 2 oscillates in simple harmonic motion with a period, there goes Vinny, with a period of 0.14 seconds, and block 1 slides off the opposite end of the elevated surface, landing a distance d from the base of that surface after falling height h. And they give me h. What is the value of d? So let's keep track of everything they tell me. This height h is given. So the sequence of events, let's be clear, is, first of all, there's no friction anywhere, so don't worry about friction. Block 1 is sliding to the right. It's got a mass m1 that I am given, and it's sliding to the right at a speed v that I am given. It undergoes an elastic collision. And let's take every word they give us as important. So there's an elastic collision between the blocks. I am told that the spring has nothing to do with the collision. But after the collision, here's what happens. Block 2, which is connected to that spring, is oscillating. Oh, let me get it apart. Back and forth with simple harmonic motion, because we've created a simple harmonic oscillator. We've got block 2 to oscillate, and I'm told what period it has for that oscillation. In fact, it is 0.140 seconds. I'm also told the spring constant K. Okay? Block 1, after the collision, has rebounded and is going back this way with a velocity I'll call V1 final after the collision. And I can tell you something right now, because block 1 has reversed itself, I know that block 2 has more mass than block 1. And then block 1 just keeps going to the left. It will get to this point, treat it as a particle, And from that point, it will just undergo projectile motion. Traveling downward, height h, and we're told what h is, 4.9 meters, so that's pretty high. But we want to know how far horizontally it goes. Well, that part right there, the projectile motion, that's just chapter 4. We can solve that as long as we know that V right there, what I'm calling V1 final. Because that's as far as the projectile motion is concerned, that's the initial V. I'm calling it the final V because it's after the collision with the second block. But as far as the projectile motion is concerned, it's the initial velocity, and that initial velocity is purely horizontal as block 1 leaves that elevated surface. So if you can figure out that V1 final, you can do the chapter 1 problem to find out how far the D is. So let's just talk about how to get that, what I'm calling V1 final. This brings in a lot of physics. It brings in chapter 4, chapter 9, and chapter 15. All right, I've already talked about how the chapter 4 is involved. The chapter 9 is from the elastic collision between the blocks. And here what we have, I'm just talking about the collision now, that's a very short period of time, a fraction of a second when the two blocks are in contact, but that's the collision. That's an elastic collision between the blocks in one dimension. And I remember from chapter 9 that if I have an elastic collision between two particles in one dimension, and we even called them 1 and 2, and particle 2 was initially at rest, then there was a set of canned formulas for finding the V's of the particles after the collision. And the one I'm interested in is V1 final. And that formula is M1 minus M2 over M1 plus M2 times V1 initial. Now, that may require you to review a little bit in chapter 9, because that's where we did elastic collisions in one dimension. But on our last midterm, this formula was somewhat prominent. So it hasn't been that long ago since we've worked with that formula. Now, this V1 initial is just that V that I've got drawn in my picture up there. And I'm told how fast block 1 is moving before it collides with block 2, and my number is 8 meters per second. That's how fast block 1 is moving before it collides with block 2. And I know the mass of block 1, M1. My number that I'm given is 0.2 kilograms. So that's the M1. If I can just figure out the M2, then I can plug into this, finish this formula and get V1 final. And once I have V1 final, I go back down to my second picture and solve my chapter 4 projectile motion problem. So now the only remaining question is, what is the mass of block 2? Because they don't say. Well, here's what they do say. Look at the second picture. After the collision, block 2 is now in simple harmonic motion on a spring, and I know the period of that motion. Right there. If I could use that information, the period of block 2's harmonic motion, to figure out block 2's mass, I'm good. And the point is, you can do that. Because what you need to remember from chapter 15 is that for a block on a spring, the angular frequency of its oscillation, which is 2 pi over its period, is equal to the square root of the spring constant divided by the mass of the thing that is oscillating. And what is oscillating here is block 2. So you would put M2, not M1, M2. Now, look here. With that expression, you have a formula to solve for M2. So you get M2 from that formula. You put it into the equation right above to get V1 final. And then you come back down and you use that V1 final to do the chapter 4 projectile motion problem. And thereby get the final thing that they asked for, which is this horizontal distance D. Now, since that's a homework problem for tonight, I'm not going to go through every step. I'm going to ask you to bring it to completion. But do you want to ask a question about any of the things I've said here? Okay, I guess there aren't any questions about that. So you see if you can put all this together, write it out for yourself, nice and neat on a piece of paper, compute the value of D, and then that's what you would enter for your answer. Okay, is there another problem you'd like to ask about? Okay, here's a question on the chat. Could you review problem 2 on the practice exam? Okay. Problem 2 on the practice exam. Let me get myself some space here. And then I'll read it. Problem 2 on the practice exam says, the figure shows a uniform disk that can rotate around its center like a merry-go-round. And so they draw that kind of a shape. You're looking down from above on this disk with the axis of rotation right in its center, and the axis is coming out of the screen towards us. This disk has a radius, big R, of 2 centimeters, we're told. This disk has a mass, big M, of 20 grams, we are told. And it is initially at rest. Since it's going to rotate, that means its initial angular velocity, however you want to call it, omega 1, omega 0, whatever notation you want to use, would be 0. And starting at time 0, 2 forces with constant magnitudes are to be applied tangentially to the rim as indicated. And the forces are shown like this. There's a force F1 tangential to the rim, meaning that's a right angle there, pointing like so. And then over here on the other side, roughly about here, tangential to the rim, is a force F2. So that's also a right angle, like so. So it's clear that F1 and F2 are competing, trying to get the disk to rotate, either clockwise or counterclockwise. All right, now, and it starts out at time 0 from rest. at the time t equals 1.25 seconds, when both of these constant forces have been acting tangent to the rim, F1 directed clockwise and F2 directed counterclockwise, at time t equals 1.25 seconds, the angular velocity, I guess I'll call it omega 2, is 250 radian per second counterclockwise, positive. Counterclockwise is positive. Okay, that's all given. That's the situation. I've got two forces trying to get the thing to rotate. It does rotate. It rotates counterclockwise. And at t equals 1.25 seconds, I know how fast it's going. Angular speed, it's going 250 radians per second. Okay, here come the questions. A, calculate the constant angular acceleration alpha of the disk during this 1.25 second time interval. Well, the good news is we are told that the angular acceleration is constant, alpha. So we get to use the constant angular acceleration equations. I'm going to use the first one. Omega final equals omega initial plus alpha t. That's constant angular acceleration equation 1, relating angular velocity, angular acceleration, and time. Now, omega 1 is 0. So let's just solve this equation for alpha then. Omega 2 over t, so positive 250 radians per second over a t of 1.25 seconds, and you get a positive angular acceleration of 200 radians per second squared. So this whole thing is going to rotate counterclockwise. That's what it's going to do. Okay, that's part A. Now let's go on to part B. Part B asks, calculate the rotational inertia of the disk for an axis through its center. Well, the good news is that that axis goes through its center of mass. And it's a uniform disk of a given mass and radius. So for a uniform disk of a given mass and radius with the rotational inertia through the center of mass, you get 1/2 mr squared. So we plug in 1/2 m. M is 20 grams. Now we got to change that to 0.02 kilograms. And then the R is 2 centimeters. And we got to change that to 0.02 meters. What do we get when we put that into our calculator? We get 4 times 10 to the minus 6 kilogram meter squared. That's the rotational inertia. And we've done part B. Okay, part C. The force F1, so we see it up there, has a constant magnitude of 0.1 newtons. Okay, 0.1 newtons. Showing all your work, calculate the torque tau1 due to F1, including the sign, tau1. Okay, I'm going to use magnitude of force times what we call the moment arm, and I need to get a direction. Remember with rotation in chapter 10, anything counterclockwise is positive and anything clockwise is negative. So a torque that would cause counterclockwise rotation is positive, and a torque that would cause clockwise rotation is negative. But here I'm looking only at F1, completely ignore F2. And there's the axis right there. So if I pull on that disk in the direction of F1, I'm going to want to produce clockwise rotation. And clockwise rotation is negative. So this torque tau 1 is negative. So I have to insert that negative sign by hand. And then I have to figure out R perpendicular, the moment arm. Well, that's the perpendicular distance from the axis of rotation to what's called the line of action of the force. Well, the line of action of the force is tangential to the edge there. And the moment arm goes out at that at a right angle. The point is that the moment arm is just the radius of the disk. So this is then minus big R times F1. So minus big R, 0.02 meters, and the F1 is 0.1 newtons. So I get minus 0.002 Newton meter. And we have found the torque on the disk due to force F1. And we've done part C. Now we go on to part D. What is the sign of the torque tau 2 due to the force F2? Sine of tau 2. Now we are looking at the torque that comes only from the force F2. And I just need the sign of it. So I completely ignore F1. And I say, which way will F2 cause the disk to rotate? That way, which is counterclockwise. Well, that's a positive torque then. So the sign of the torque tau 2 is positive. And I've done part D. Part E. Calculate the magnitude of the second force, F2. Show all your work. Well, I know I have to show my work. Okay. So how do I get F2? That's what it all boils down to. What's that magnitude? They've told me everything else. They've told me the magnitude of F1 and the radius of the disk. That's how I got tau 1. They told me the mass of the disk and the radius. That's how I got ICOM. I figured out alpha, the angular acceleration. What physics idea is left to get F2? Well, we're clearly talking about rotation. We've got one of the two torques, one of the two. We've got the angular acceleration. Let's use Newton's second law, angular version. Angular acceleration alpha equals net torque over rotational inertia. In this case, for the axis to the center of mass, net torque. Now I've got two torques, tau 1 and tau 2. So that's what I have to put there. Now don't worry about the tau 1. I've already figured it out. Negative 0.002 Newton meter. That's done. For the tau 2, well, let's write out a little bit more about that. The torque tau 2 would be the force F2 times its moment arm, which is another factor of big R. That's the moment arm for F2. So if I look at this formula, I know alpha, I know tau 1, I know R, I know ICOM. I know everything except F2. So let's solve for F2. Okay, let's multiply by ICOM, both sides. So ICOM alpha equals tau 1 plus F2R. So then ICOM alpha minus tau 1, all divided by R equals F2. So I just did my algebra there and solved algebraically for F2. For ICOM, we enter 4 times 10 to the minus 6 kilogram meter squared. For alpha, we enter 200 radian per second. For tau 1, we enter, be careful, negative 0.002 Newton meter. And for R, we enter, be careful, convert it to meters, 0.02. Note in this numerator, you've got a negative multiplied by a negative. So that's going to end up being positive. And the number I get then for the magnitude of F2 is 0.14 newtons. Now I know that that F2 magnitude that I just got right there has got to be bigger than the F1 magnitude, and that was 0.1 newtons, because the whole thing rotates counterclockwise, and that's the way F2 wants to go. In other words, F2 is winning. So yes, F2 is going to have a bigger magnitude than F1. And what we found is that F2's magnitude is 0.14 newtons, and indeed bigger than F1's magnitude. Okay, that's practice exam question 2. Any questions about how I did that? Scroll back this way, okay?
Real quick, could I just have a refresher on like what counts as torque acting on a rotating object?
So in general, I'll scroll this up just a little bit. Hopefully I won't take out of view what people need to see. If I have some object, I'll talk more along the lines of chapter 10 for right now. If I've got some object, I don't even really care what shape it is. I'll make it a shape of kind of like a lima bean. And I've mounted it on some kind of axis of rotation. This axis, I draw it like a dot. You're supposed to imagine an axis like the hinge of a door that's coming out of the screen towards you. So this lima bean can rotate in the plane of the screen, either clockwise or counterclockwise. And then what I do is at some point, I really don't care where, maybe right there, I grab hold of the thing and I apply a force. I don't know, maybe in some direction like that. Okay? I contend that by taking that object with its given axis of rotation and applying that force at that particular point, I will cause that thing to rotate about that axis. And the measure of the tendency of the force to cause rotation is what torque is. And the way we calculate torque, symbol Greek letter tau, is in chapter 10, take the magnitude of the force times what's called its moment arm. You need two things to have a torque, a force and a moment arm. So let's review that. There's my force. How do I find the moment arm that goes with that force? The procedure is just extend the force arrow line in both directions. You may need to, like that. That's called the line of action of the force. That's not the moment arm yet. Here's how you get the moment arm. The moment arm, what I'm calling R perpendicular, and there's a reason that subscript perpendicular is there. The moment arm is the perpendicular distance from the axis of rotation to the line of action of the force. So I have to draw a line that starts at the axis and hits that green line at a right angle. And here I'm just going to have to eyeball it, but it's going to be something roughly like that. You see what I mean? It's got to hit the line of action at a right angle. It would be very clearly incorrect to draw something like that and try to call that the moment arm for that force, because that red line clearly does not intersect the line of action at a right angle. the moment arm must intersect the line of action at a right angle. Okay? And so it's that distance I've just sketched there. Now, there's going to have to be information given to me in the problem somehow to figure out what that distance is. Here's a common thing they'll do. There's another vector that you'll often see in this drawing, so I'll draw it now. And it's confusing, and that's why I think people struggle with it at first, but it's not the moment arm. It's not in general. This vector points from the axis out to the point where the force is acting. And that's just a plain old position vector, R arrow. And R arrow points from the axis of rotation out to where the force is acting. Okay, so there's kind of my completed picture. Now to calculate this torque, I will need to know the magnitude of this force and this distance. Now, here's one way you might be given this as a problem. You might be told the magnitude of this force outright. Let's say it's 2 newtons, just to make something up. You might be told how the magnitude of R, that R. You might be told that that magnitude is some number. I'll make something up. 0.75 meters. That's the length of the R vector. That's still not the moment arm. And you would likely be given that angle right there. I'll call it phi. Maybe you would be told that phi is 20 degrees. Now you have enough information to get the torque. Because what you have to be able to see from trig and geometry is that the distance you need, the moment arm, R perp, can be found from trig because I have a right triangle right there. And R is the hypotenuse, and the moment arm is one leg. And it's the leg that's opposite to phi. So R perp is hypotenuse sine phi. So that's 0.75 meters times the sine of 20 degrees. And that turns out to be, I kept the degree mode, 0.257 meters. That would be the moment arm in that case. Now let's go back up and finish this off by getting the torque from that force. By the way, I'm not quite done with the torque formula. There's another important part. Direction. In this kind of a picture, the force is going to cause either clockwise rotation or counterclockwise rotation. Those are the only possibilities. You have to be able to look at this picture and tell which it is. So you have to be able to look at this thing, you have to see where the axis is, see where the force is pulling and which way the force is pulling, and realize, oh, this force is going to want to produce rotation that way, clockwise. And clockwise torques are negative. So I have to insert a negative sign by hand here. And then I'm ready to finish off the torque calculation. So the torque will be negative moment arm, 0.257 meters times magnitude of force, 2 newtons. So I take those, multiply them, and I get negative 0.513 Newton meters. And we have calculated the torque on this object due to that force about the specified axis. And that is a somewhat typical torque calculation problem. Oh, somebody else wants to be admitted. Does that make any sense? Does that help any with just kind of solidifying understanding of torque?
Yeah, thank you.
Okay. Okay, another question. Anything anybody would like to ask? You can either unmute or you can type it in the chat box. Okay, problem 1 on the practice exam. Okay. All right. Practice exam. Number 1. Okay, this is the falling chimney problem, which I think I showed a video of at one point in a video lecture of a falling chimney. So in this problem, we have a chimney. It has a given length, happens to be 40 meters, because these chimneys tend to be rather tall, and a mass M. And it's initially vertically, as shown in part A of the figure. So let me try to draw that. That's just the ground. Let's just represent the chimney as a rod or a cylinder. And there's going to be an axis down there at the base. It's going to rotate about that. That's my initial picture. And the chimney has a length L, which is 40 meters. Okay, and a mass M, although they don't tell me a number for M. But it's got to have some mass. We'll just put M. Don't assume a value, a number, just label it M. Okay. The chimney is given a very small initial angular velocity, infinitesimally small, just enough to get it going. And it falls to the ground by rotating about a fixed axis at its base. There's the axis. You were to imagine that as like a line coming straight out of the screen towards you. Okay. Part B of the figure shows the chimney during the fall when it makes angle theta with the vertical. Let me draw that. So there's the axis. There's vertical for reference. And the chimney is still just a rigid cylinder or rod of length L, but it has now rotated through an angle theta measured to the vertical. Let me mark the center of this chimney right here. That's where the center of mass will be. And so that's where it would have started right there. And it will follow a circular arc. And now the center of mass will be there. And at this moment, when I've drawn this picture, the angle between the line of the chimney and the vertical line is theta. We are to model the chimney as a uniform rod with its center of mass at its center. because the only force doing work while the chimney falls is the gravitational force, the mechanical energy of the chimney earth system is conserved. So we're telling you the important physics principle here. So here come the questions about the falling chimney. First question, part A. What is the symbolic expression for UG1, the gravitational potential energy of the system at instant 1? Oops. That's instant 1. This is going to be instant 2 over here. We are to find a symbolic expression for the gravitational potential energy at instant 1. We are told that this will be a symbolic answer, no numbers, in terms of M, the mass of the chimney, G, and L. And they give me a hint. I never ignore a hint. Observe that the figure shows the location of y equals 0 at ground level. Oh, it does. It shows a plus y axis going up and y equals 0 on the ground. I have to be consistent with that then. Okay, well, remember the formula for gravitational potential energy. And I recommend you don't say mgh. I said that in class in chapter 8. It's mgy, mass times g times the y coordinate. But this chimney is not a particle. It's an extended body. So what's the appropriate y coordinate to use? Answer, the center of mass. So what's the y coordinate initially? It's that much right there. How high is that above y equals 0? L over 2. So UG1 is mg y center of mass in picture 1. So that's mg L over 2. And now we have an expression for the initial gravitational potential energy of the system. And we've done part A. So let's go on to part B. B, what is the symbolic expression for U grav 2? Probably should have seen that coming. The gravitational potential energy of the system in picture 2. This will be a symbolic answer in terms of M, G, L, and theta. Well, now I'm focusing on picture 2. But I'll start with M, G, Y, C, O, M for picture 2. Now let's be very clear about how we're going to get that. YCOM for picture 2 is that height, which if you want, you can go straight over perpendicularly and draw it right there if you want. That might be a little bit more helpful. Why? Because this distance along there from the axis to the center of mass is L over 2. This angle right here is theta. And I want that length right there. But that length is L over 2 times cosine theta. So this is M times G times L over 2 times cosine theta. Picture is worth 1,000 words there. The picture is what's going to help you see what to put there. But that's part B. Purely symbolic. No numbers yet. Won't be numbers for a while. Let's go on to part C. Part C says, derive the symbolic expression for I sub A. The axis there is A, right there. That's the rotational inertia of the chimney about the axis A. It will be a symbolic answer in terms of M and L. Hint, never ignore a hint, the rotational axis does not pass through the center of mass, right? Axis A is down at the bottom of the chimney, not through the center. So what do? we use the parallel axis theorem. The rotational inertia through the axis A, which is at the bottom of the chimney, is given by the rotational inertia for the axis through the center of mass, plus what your book would write as m times h squared. That's how your book would write the parallel axis theorem. What do they mean by that second part? Well, the m there is just the mass of the thing, in this case, the chimney. What is the h? Got to be able to understand that h. The h is the distance between the axis you have, in our case, the axis at the bottom of the chimney, A, and the axis through the center of mass. So what you have to be able to see in our case is that the h they want you to use, in this case, is L over 2. Now, what do we use for this ICOM? Well, now that's a common enough expression that we can get that from that table in chapter 10. Because this is just a uniform rod of mass m, length L, and for the ICOM, axis through the center of mass, that is 1/12 ml squared. That's the ICOM. So I take 1/12 ml squared plus m times h squared, where h is L over 2. So this is 1/12 ml squared plus ml squared over 4. And now let's factor an ml squared, and we're left with a 1/12 plus 1/4. But we can add those two fractions by getting a common denominator of 1/12 of 12. So that's 1/12 plus 3/12. So that's ml squared times 4/12. That's ml squared over 3. That's the answer for C. That's the rotational inertia of the chimney for the axis A down at the base. And that's part C. All right, part D. You may assume, it says, the initial angular velocity at instant 1 is so small that the rotational kinetic energy K1 is 0. Using conservation of mechanical energy, solve symbolically for the angular speed of the chimney as a function of G, L, and theta. So here I want to see you start with this expression. E mechanical 1 equals E mechanical 2. I'm not really looking for anything other than that as a starting point. If I say use conservation of mechanical energy, or you decide for yourself, I'm going to use conservation of mechanical energy, then that's the starting point. Now there's a question here, L over 2. You mean for the H? So here I'm using the parallel axis theorem, okay? That's what this is right here. Oh, you were answering me. Got it. Very good for you. Thank you. Okay, very good. Okay, so now we're proceeding on to part D. And I was saying that I want you to start, if you're going to do conservation of mechanical energy, that's what I want to see you start with. And so let's start with that. The next step is to write this, K1 plus U grav 1 equals K2 plus U grav 2. And if we had a spring as well, thank goodness we don't, but we'd have to have a US1 and a US2 added in there as well. Now, I'm told I can set K1 to 0. Fine, I'm happy to take anything that simplifies it. But the other ones aren't 0. So let's write down symbolic expressions for all the other energy forms. Well, you can see, I hope, that this problem is setting you up step by step. We did in part A, we got an expression for U grav 1. There it is, mg L over 2. So for the U grav 1, mgl over 2. Okay, next, K2. Well, now we're talking about picture 2. Please note, picture 2 shows the chimney in mid-fall. It's rotating, right? It's not going to stop there. That's just a picture we happen to draw. It's some arbitrary moment during the rotation. And it will have some angular speed, omega, at that moment. And if it's rotating about an axis A, then the formula for the kinetic energy, rotational version, is 1/2 rotational inertia for the axis A times omega squared. You don't need the absolute value really because it's squared, but I'll write it. Plus U grav 2. Well, we did that in part B. mg L over 2 cosine theta. Okay, now let's start substituting in things and solve for omega. That's what we're going to do. That's the plan. So let's see what happens. Let me do that. Okay, I've got I'll write it over here. mg L over 2 equals 1/2 I sub A. Let's put that in. mL squared over 3 times omega squared plus mg L over 2 cosine theta. Every term has an m, so let's divide both sides by m. Now that's why they didn't give me the m value. They didn't give me a number for the mass. Now I see I don't need to know it. Then I have GL over 2 minus GL over 2 cosine theta equals 1/2 times L squared over 3 times omega squared. Let me multiply both sides by 2. That gets rid of all those down there. Let me factor G times L on the left. Then I have 1 minus cosine theta in parentheses. And I have that. Let me multiply by 3 and divide by L squared. Oh, I can divide both sides by 1 factor of L. So let me multiply by 3 and divide by L, and then take the square root. And I get this. 3g over L times 1 minus cosine theta, all inside a square root. And that is the symbolic expression for the angular speed of the chimney as a function of the angle theta. You tell me where what the theta is, and I can use this formula to tell you how fast it's rotating. That's part D. Part E. Using your answer from part D, calculate the angular speed of the chimney when it just reaches the ground. Okay. I'll do it right here. If the chimney has just reached the ground, it's just coming down on the ground. Now don't say 0 because it hasn't collided with the ground yet. So it's just become horizontal. The point though is that the theta then is 90 degrees. Remember, the theta is measured from the vertical going up. So the angle here is 90 degrees. So you plug in 90 degrees for the theta there inside the omega formula. But the cosine of 90 is 0. So the angular speed when it reaches the ground is just the square root of 3g over L. That's all that's left. Plug in g, of course we know that. The L we're told is 40 meters. So when I put 3 times g divided by L, and don't forget to take the square root, I get 0.857 radians per second. And that's its angular speed just as it reaches the ground. And there's one more part, F. F asks for us to calculate the linear speed of a point on the end, the tip of the chimney, just as it reaches the ground. Okay, so now we're focusing on that point right there on the tip. And if you look at a point on a rotating body, you can ask what its linear speed or velocity is. V, not omega, V, linear speed. How fast in meters per second is the point on the tip moving just as it comes to the ground? Again, don't say zero. But what you do want to say is the magnitude of V is equal to the magnitude of the angular speed omega times the distance of that point from the axis of rotation, which in our case is L. So I take omega times L. And that will be how fast in meters per second the point on the tip is moving. So for the omega, you put in the 0.85 radians per second, we just found in part E. And for the L, 40 meters. And you get a pretty high rate then for V, 34.3 meters per second is how fast the point on the tip is moving. And so if you watch YouTube videos of chimneys in demolition, tall ones, you can find YouTube videos of very tall chimneys being demolished. They start out very slowly, and then they go faster and faster because gravity is pulling them down. And if you look at the point on the tip, you can discover that just as it reaches the ground, point on the tip is moving pretty darn fast. You wouldn't want to be near that thing as it is being demolished. Okay, so that's the falling chimney problem. Any questions on anything I did there? You're welcome. Any other questions about any other problems? Okay. Well, thank you for those that were able to make it. I have recorded this, so I will upload it. Well, I'll send a YouTube link to everybody so that people can see it. Good luck tomorrow. Don't forget to set aside sufficiently long chunk of time that you can work slowly and carefully on the exam. And yeah, good luck. I'll be sending out lecture videos for Thursday soon. Make sure you get a good night's sleep if you can.